So on behalf of the many committed faculty, students, and faculty, staff, and students who are members of the Rutgers Science Communication Initiative, I'm pleased to welcome you to the third in an ongoing series of events focused on advancing the science, teaching, and practice of science communication. I'm Bill Hallman, professor and chair of the Department of Human Ecology. Here with my colleagues Nick Ponzio and Mary Nucci, who are leading the Science Communication Initiative. To those of you who are joining in for the first time, I'd like to say welcome. To those of you who are joining us again, I'd like to say welcome back, and would like to introduce the moderator for this evening's session, Dr. Janet Alder, Assistant Dean of Graduate and Academic and Student Affairs in the Graduate School of Biomedical Sciences at Robert Wood Johnson Medical School. So that's a mouthful, and I'm sure it fills up your card, Janet. So with that, please begin.
Thank you, Bill, for the introduction and for your efforts along with Mary and Nick and everybody on the Science Communication Initiative. It's a very important program, and I think I wasn't able to attend the first one, but I attended the second event, and I thought it was really a very fruitful discussion, and I definitely learned a lot. So I hope everybody feels that way after today's session as well. Today's topic is something that's very close to my heart because I am one of the co-directors of a class in communicating science along with Nick Ponzio, and Mary works with us on that as well. And so the topic is really about education in science communication. And we have three people who are equally passionate about science communication education with us today on our panel. So we have Ravit Duncan, who is Associate Professor of Science Education at the Graduate School of Education. Mary Nucci, who is Assistant Professor in the Department of Human Ecology at the School of Environmental and Biological Sciences. And Nick Ponzio, who is professor in the Department of Pathology, Immunology, and Laboratory Medicine at New Jersey Medical School. And each one of them represents a different phase in terms of the lifespan of science education. So Ravit is involved in studying K through 12 education. Mary is particularly involved in undergraduate education, and Nick in graduate student education. So I'm going to start off by letting each of them tell us a little bit more about themselves and their role in science communication education. So Ravit, if you would like to share your screen and tell us a little bit about your path.
Yes, so I hope everyone can hear me. Hi, everyone, welcome. I'm Ravit Duncan. I am at the Graduate School of Education in the School of Environmental and Biological Sciences. I have a joint position. My research is in science education with a focus on epistemic cognition. And since this word is going to come up a lot, I'm going to define it. So epistemic epistemology is a field that studies how we know what we know. Essentially, in relation to this talk, is how do we know that information, a claim, is valid, reliable, trustworthy? How do we figure that out? So a large part of what I do at the Graduate School of Education is figure out how can we help students, and by students I mean K-12, mostly secondary students, that's middle and high school. How can they become better at reasoning with and about evidence? I design learning environments in science education. I do a lot of professional development with teachers around this issue in New Jersey, nationally, and some international work. And I also coordinate the biological science certification program. So I prepare secondary biology teachers. So a couple of important things. We live in what's been determined, what's been called a post-truth world, right? There's a lot of misinformation out. It's very difficult to tell what is and is not true. And there are multiple reasons for this. Partly it's cognitive biases and motivated reasoning. We hear what we want to hear. We tend to agree with information that agrees with the points that we see as true. There's a lack of knowledge about how scientific information is generated in labs, how scientists go about building knowledge, and poor strategies for evaluating information in the media by students and lay individuals. There's a devaluing of expertise, right? The idea that everyone's an expert now. And people hold different epistemic criteria for determining trustworthiness of information. And what I mean by that is that scientists have a set of norms, what we call epistemic norms, for how they know, what counts as a good theory, a good evidence, good explanation. And individuals may hold epistemic criteria that are different than that. They may prefer to trust their gut or an anecdotal story from their aunt about something rather than trusting expert consensus. And current instruction falls short of addressing these problems and in some ways contributes to some of them. So what we've been trying to do is help students develop what we call a lay grasp of evidence, help them understand both how experts generate and evaluate scientific evidence within a scientific community. That's what we call experts' evidentiary practices, and understanding lay people's evidentiary practices. So lay individuals simply do not have the disciplinary, the content knowledge to reason about the kinds of evidence, models, theories that appear in scientific journals, or even in some cases in the media. So they're bound to disciplinary knowledge, and the question is, well, what can they do? What can we lay individuals do when we're trying to negotiate claims and evidence that we see? And this is work that's been done with my colleague, Clark Chin, also at the Graduate School of Ed, and Sarit Barzilai, who is at the University of Haifa. And my main message today, if you take anything away from what I say, is that students are ill-prepared to reason with evidence in the wild, outside of the science classroom. If we want them to be able to reason with epistemically messy evidence, the kind of evidence you find in the wild, in media, social media, and the news, we need to engage them with that kind of evidence early and often. And that is it for me.
Thank you very much, Ravit. And we will definitely be diving into more of your research and your messaging that we need to take home. And I just want to remind people that throughout today's webinar, if you have questions, to please type them into the Q&A feature at the bottom of your screen, and I will be asking them of the panelists. So moving from K through 12 to undergraduate, Mary, can you please share with us your role?
Certainly. So let me get the slideshow up. So I'm going to tell you a little bit about myself and my path and trajectory, which will probably help as we're going through the talk and the questions. So I am an assistant professor in the Department of Human Ecology and SEBS, and the assistant dean for community engagement also at SEBS. My background is I am a scientist in biological science and zoology, and a PhD in communication. My research spans two completely different kind of directions. One is at the bench, where I was involved for many years in the immunological studies on two products, which now are approved drugs, and then later on segue to really being concerned about how we come to understand science and what people, why do people not love science as much as I do and love reading textbooks and way before PowerPoint overheads and all those things. So my research over the last 10 years has focused on these issues of perceptions of science in mass media and museums, science learning, interest and identity, and science visuals. In terms of communication, which is prior to my being a professor here at Rutgers, I was a freelance science writer for many years, where I learned how to communicate science more effectively to the public, moved into museums. I was the director of the Health for Liberty Science Center, and currently here at SEBS, I direct the Science Cafe series, which is in its 5th year of programming. And in terms of teaching, I teach at SEBS. I teach a number of courses out of the Human Ecology department, all focused on science communication. I teach over at the School of Arts and Sciences in the Life Sciences, Biological Sciences school, where I've developed and co-teach now a course in writing for honor students, and teach with Janet and Nick in their class to graduate students at the graduate school. In terms of teaching and pedagogy at Rutgers, I also developed and directed the minor in science communication and the minor in science outreach. So it was important to kind of set the stage for me, because I am a scientist who's gone rogue a little bit, have left more experimental science to social science. And I don't find that there's really a difference between them, except perceptions of what other people think of science and social science. But we're all to the same aim of generating knowledge. And that, as Ravit has already referenced, the issue with knowledge as in evidence is that it's very difficult for people to understand it if they don't have the training and the background in order to understand it. So I just wanted to tell you a little bit about my teaching and my focus, and what I believe is how I think science communication should be taught. So all of my classes involve something that is real, in that it is not about writing papers. And I know a lot of my students are listening to this right now, and hopefully they will agree that it's not about writing papers, but it's about doing real work that engages them in science communications, so that they can show they can do it, but they also learn how it's done. And so these are three just very different kind of tacks I take for this real work in a classroom. So students in my classrooms often do institutional review board approved social science research, or in this case, this is media research that has been presented, submitted and accepted and presented at conferences. We have drafted papers, and we haven't quite figured out how to get them published yet. We haven't taken it that far, but we have had students present their work at conferences. Students also work with clients, and they mimic the experience of a client relationship, where they work with the client to create, in this case, it's blogs for the Lower Raritan Watershed Partnership. Work with the client gives them a goal and a task, and the students have to work with the client, making sure that their publication, which becomes then a product of the Lower Raritan Watershed blog, meets the goals for the client. So that's both it's a classroom experience in writing and communication, but also in working in a situation that mimics the real world. And a new trend, or new track that we're working on, is communicating Rutgers scientist research. In this case, this is a comic for 5th to 8th grade students based on real research. It's not necessarily always published, but it's often a review of a scientist's research to explain why a scientist does the work they do, and then also profile that scientist, so that students in 5th to 8th grade can actually see the research, meet the scientist as much as they can, and then students here at Rutgers are learning how to communicate science more effectively to the public. So that's just a little bit about me. So thank you, Janet.
Thank you, Mary. And just to make sure that everybody understands what the term lay means before we go any further, because we're going to be using that a lot. When we say lay audience, we're referring to people who are not trained as scientists. So sometimes we assume they have like a college level education, but not necessarily in science. So that's the working definition at the moment. And Nick, would you please tell us a little bit about you and what you do?
Sure, happy to do that. Let me share a screen. In the meantime, welcome everybody for joining us this afternoon. Okay, so a little about me in a nutshell. I'm a New Jersey born, raised guy. Did my undergraduate and master's at Seton Hall University. I crossed the river to go to Brooklyn. Actually, I crossed 2 rivers to go to Brooklyn for my PhD at Downstate Medical Center with postdoctoral fellowship research at the Albert Einstein College of Medicine and NYU School of Medicine. Areas that I'm interested in are in cellular and molecular immunology. So I'm a scientist. I mean, and I, over the years that I have been in academia at Northwestern University, which was my first paying job, and later at UMDNJ as in the department that Janet said, in Pathology, Immunology, and Laboratory Medicine. And in 2013, as you know, we merged with Rutgers University, and now we're one big happy family. But I've trained. I'm a lab bench scientist, like Mary said. I've trained about 32 or 3 Ph.D. and postdoctoral fellows. And after all that time, I figured I wanted to do something different. And I thought about it for a long time and decided I wanted to teach students how to communicate the really cutting edge research they're doing in ways that was not only accurate, but understandable. So I took a sabbatical. I went to the Alder Center for Communicating Science at Stony Brook University to learn how to do it. I always thought I was a pretty good communicator, but I wanted to learn from experts. And that was the genesis of a course that that I, Janet, Mary, and a couple of other people developed for PhD students called Communicating Science. I got a small grant from Burroughs Wellcome Fund that allowed me to recruit several faculty from different schools of Rutgers, including Janet and Mary. There is a faculty member from the School of Communication and Information, and this guy, who's very important, because what they do at the Alder Center that I found most important in teaching our scientists how to communicate better is to use improvisation as part of the training. And my colleague, this is Dave Dannenfelser. He's from the Mason Gross School of the Arts. He's a playwright. He teaches actors in the theater arts department. And he has a very important role in developing the ability of our students to understand that, hey, there's an audience out there. And I really need to engage them if I want to get whatever I'm telling them across. So this was a course for PhD students. We've been doing this since 2017, the first offering. I think it's been very successful from the feedback we get from students. But, you know, these are PhD students. They're one segment of a very large university. So Dave and I decided we would branch out, and we developed another course for master's level students that we gave for the first time last fall, and another course called Communicating Science and Medicine. These are master's students who aspire to get into medical school, dental school, or graduate school. And first time around, I think it went very well. But again, that's only 2 segments of the university. And the other segments, the postdocs and faculty, don't have time to take courses. So we developed a workshop format with content that is very similar to the courses that we give, Improv to Improve Communication Skills. It's a series of 4 workshops over 1 month, once a week for 3 hours. And that's been going very well. We offer that. I want to put a plug in for the Science Communication Initiative. They host the Improv to Improve series. So if you have a group or students that you think might be interested in a workshop in this area, please contact me or Mary, and we'll set something up. So that's my my pitch.
Thank you. And we can put a pitch in at the graduate level communicating science class will be open for registration in about a week.
All right.
Okay, so thank you all. And the way the rest of the webinar is going to run is that I have some questions that I'm going to ask the panelists. They'll each answer them as appropriate, but then I encourage everybody who's on the webinar, and we have 61 attendees, to ask questions of the panelists themselves and to make this as engaging and interactive as possible. So first off, let me start with Ravit. Why do you believe that we need science education at the K through 12 level? You muted.
Yeah, I just noticed that. So as I said in the intro, we're at a time where there's a lot of information. We know that fake information travels faster and wider than truth. The Director General of the World Health Organization claimed that fake news spreads faster and more easily than this virus and is just as dangerous. So it has really become very, very clear, especially now with a pandemic, that it is important that we have a public that can understand communications that are with science content. They don't always come from scientists, but have science content, can evaluate them and knows how to respond and react. And given the prevalence of social media, some of the traditional gatekeeping features of what would be more traditional news outlets, science journalists, that doesn't exist on social media. So some piece of information gets in there and then it spreads like wildfire, and it could be entirely false. It could be misinformation that's just something that's wrong, or disinformation, something that's out there with the intent to deceive. And that's dangerous. Without exposure to and learning how to navigate this space, this new information world, we're going to keep this cycle up of citizens, individuals who are unable to tell fact from fiction, unable to respond appropriately, make all sorts of decisions that both put them in danger, but also put others in danger, as we've seen with the pandemic. So that is that's to me what is most important. We need to have citizens that are, I'll use that word again, epistemically vigilant. People who can critically evaluate and understand the kind of information, science information that's available. And critical is a really important word here, right? They need to be vigilant in terms of knowing, how do we know and why do I trust this information, and do I have a basis for trusting it?
Okay, so at the earliest, youngest ages, we need to start this process.
Yes. And you can do that from elementary. There's nothing that prevents even young children from engaging with some of these issues. Even young 4th graders and 5th graders can think about issues like confounding factors in an experimental setup.
Thank you. So Mary, what do you believe is the impetus for creating science communication education at the undergraduate level?
So because we are this K through postgrad, I build definitely upon Ravit. So everything that Ravit said is absolutely follows through in the undergraduate realm. But one of I think the factors that's really important, especially at the undergraduate level, is that once you leave formal education, unless you are engaged in science or have a deep-seated interest in science, you no longer learn any new science. And we know that what people then start to depend upon is their group that they ally themselves with, whether it is a religious group, whether it is a political group. And it's very difficult for people to change their minds once they aren't aligned with the group. So if we do not have that underpinning Ravit is talking about at a K to 12 level and continue to build on that at the undergraduate level, people will not be able to go out and really understand evidence, know how to use evidence, and then they will listen to a group. They'll do a group think instead of an individual think. It's a challenge to change your mind, And we do also know that the more science you know, a lot of times the less likely you are to be able to change your mind about science. It's kind of like a little knowledge is a dangerous thing as regards science. It becomes very problematic. So for the undergraduates, it's building upon, we would hope it's building upon what people like Ravit are doing to try to demonstrate that this is critically important, but then to extend it to understand, to develop a sense of confidence that you can actually understand science, or if not understand science, understand the materials, how to use the materials to get the information you need. You don't have to be able to understand all the nuances of nanotechnology and genetic engineering and synthetic biology, but you have to know where you can go, who you can trust as an expert, where you can go for the information and access it, and how you can interpret that information. Some of that is confidence building at the undergraduate level, which they can then carry forward into their private lives once they graduate from school.
Thank you. Informed citizens is what we need. And Nick, at the graduate level, what is the role of science communication education?
Yeah, this is, it'd be easy for me to say it's Ravit's fault and Mary's fault for not producing people who could do the things that they aspire to do. But the fact is, these are highly trained people that get into graduate school. And I was somewhat surprised when I made a survey. There's not a lot available to actually teach our PhD students and postdoctoral students how to communicate. There's a lot of writing courses, a lot of writing workshops. There's very few that focus on oral communication. And these people are going to be talking to a lot of people in different diverse audiences, and they should know, there should be training in for all the science programs, at least I feel, that's my opinion, in how to get up and give a talk, whether it's a 3-minute speech, which we do in our communicating science course, or a formal seminar. And you know, I've been around a long time. I've sat through a lot of seminars, a lot of thesis defenses, and I can tell you, great work, could do a much, much better job of communicating not only what they do, but why they do it, why the audience should care about what they're doing. If you can tell people why you do it, maybe they'd appreciate why they should do it, and why they should care about what's the significance of what they do. So those are some of the things we focus on in our course. And we give them plenty of opportunity to practice their talk. We ask them to do a 3-minute speech, as Dave calls it. And we work with them on that 3-minute speech for the entire semester, and hone it into a very scientifically accurate, but an engaging and understandable rendition of what they do. And that's what I think we need to integrate into science programs at the graduate and even postgraduate levels. I'm very happy to tell you that there is one program that now has required a communicating science course into their program, and that's a program that was awarded last year to Rutgers, Princeton, and NJIT, a $40 million grant on clinical and translational science. The fellows in that program now are required to take communicating science so that they can do exactly what I said, be able to explain what they do, its significance, and to diverse audiences.
Thank you. So we can really see from the youngest kids being consumers of scientific information to Nick's level, where they are the producers and therefore disseminators of scientific evidence. the need for nuanced education at all levels. So Ravit, going back to you, if you could share with me, you know, what are the top 3 learning objectives that you would say some student in K through 12 would need to have in relations to science communication and understanding?
Right. So there are several things. One is students need to have a much better understanding of how the scientific enterprise works, right? So if you look at most textbooks today, you will still find your generic step-by-step scientific method that suggests that if you just follow these steps very closely, like a recipe, the truth will unproblematically emerge from the data. And that's just not how it works. First of all, there is no single scientific method, and it is absolutely not linear, and nor is it this sort of unproblematic emerging of understanding. Science is a human endeavor. It's social. I think if one of the things that is really important to emphasize in K-12 settings is the role of the community in vetting scientific knowledge. So many students don't know what peer review is. They've never heard of this. So when they get information about COVID and someone says, well, it was published somewhere, it's not, you know, it hasn't been peer reviewed yet. I would argue that many lay individuals don't really know how to make sense of that information. Why is that relevant? Why is that important? So understanding the community processes that are involved in vetting scientific information is really important. Understanding that they have limited knowledge, and this goes back to, no, you're not an expert, right? Not everyone is an expert. You can reason about things, and I think this goes back to the point that Mary raised, that one of the phenomena we see is that the more knowledge you have, meaning the more education you have, the better you are at what we call motivated reasoning. Motivated reasoning is directional reasoning. If I believe something and you give me a piece of evidence that contradicts that, I will figure out a way to kind of interpret it in light of my belief or dismiss it in light of some argument that I might have. And the more schooling you have, the better you get at that. So what we're actually teaching kids in school in some ways, they are getting better at reasoning and better at arguing, but they're not realizing their bounded knowledge. And they also don't realize that they might have different norms for evaluating that knowledge. So in science, fit with evidence is an absolutely critical norm for deciding whether a model or an explanation is worthwhile, what's the merit of that explanation. And not all evidence is created equal. Some evidence is better than others. And when you have lay individual students who don't understand that and consider anecdotal accounts to be just as good as statistical evidence, where they trust their gut about what they should or shouldn't do with their children in regard to vaccination or their own group, as Mary was saying, because they belong to some group that's against that vaccination rather than listening to scientific consensus in this area. So the epistemic norms that they use to evaluate information, a norm like I trust my gut, I trust my group, those are not the norms that scientists espouse. So understanding what are the kinds of considerations that scientists have for knowledge is really important. And lastly, media literacy. They really need to understand the points that Nick and Mary were saying about how information gets transformed from the lab, right, from test tube to YouTube. That is absolutely critical, and you don't see much of that in the science classroom right now.
I like that, from test tube to YouTube. I haven't heard that before.
That's not me, that's Doug Alchin. Credit where credit's due.
Excellent. Thank you. So Mary, what would you say are the top 3 learning objectives in the courses that you're involved in for undergrads?
So I'm going to pick up again on Ravit. I think it's going to be this way all night. So the first thing that's not necessarily learning objective, but is to understand that what the students are, when they come in, what's their baseline of knowledge, especially as regards the nature of science and the scientific process. And so there's just some kind of testing to see where they are. And I'm happy to say that the majority of students get that. So once we have that, once they have that knowledge, then we can go and think about the learning goals. It's these practices of science and communication that become very important, that you understand how science is disseminated and who are the gatekeepers. And the gatekeepers are media sources. And how is that information changed as it moves from the scientific discipline to the public audience? And Ravit and I were talking yesterday, and we both used the word hedging, and that in science you hedge, because science is never done. Science is never complete. You're always building upon knowledge, but it's very true that science is also never done until it's communicated. And when it's communicated as hedged information, because you can always do more research. You've never finished it. And students need to understand how science moves through the spectrum from the bench to the public, and then understand that and become critical evaluators. So that's a learning goal. Can you critically evaluate science? Can you critically think about science? And that's also builds upon this comfort level and ability to access and use science. I think the second is to start developing a sense of who you're communicating to, or who, if you're talking to someone, how you communicate to them in a way that they will listen to you, so that if you need to challenge somebody's science knowledge, you need to think about, this person has this specific ideology or beliefs. How can I explain it or talk to them about science in a way that doesn't challenge it? Because as soon as you challenge people, you end up, they shut down and they're not going to listen. So learning how to dialogue about science would probably be the second learning goal that I think is really important. And then the third is maybe not a learning goal, but it builds upon the others, but it's this idea of practice, and that students have to experience actually communicating science. It's great to talk about it. It's a wonderful thing to say, well, if we all talk communicate science, it would be great, but you have got to practice it. And it's a beginning practice at the undergraduate level. If you only take one class, it's not something that people do naturally necessarily, but it's practicing and beginning to practice and becoming then engaged with it. So it's, for me, then it's this critical thinking based on comfort and ability to access and use information. It's this idea that you need to develop a sense of how to talk about science, how to dialogue with an audience about science, and then you need to practice it. So I know they're not specifically goals, but I think that's what's critical for the undergraduate level, Janet.
Thank you. And I think, as you point out, even if somebody doesn't continue in science, having experienced firsthand that transition from real data to how they communicate it out will give them an appreciation later on for what has morphed in those steps, potentially. Nick, do you want to share with us what are the top 3 learning objectives of your graduate courses?
Sure. That's tough to do 3, but I'll try, because students at the graduate level kind of do what they see. And what they see are people getting up, showing table after graph, talking about data, and not a lot else, a little history. But what I think the 3 takeaways, you have to engage the audience. I mean, and Mary referred to that. It's not only, there's a speaker and a listener in the room, or many listeners in the room. And it has to be a dialogue. It doesn't have to be an oral dialogue. We teach them to read nonverbal cues of the audience. You can tell if what you're saying isn't getting through, and you should be able to stop, take a step back, say, maybe I should explain that another way. Use metaphors, use examples, use analogies to explain complex things. And we want to make them comfortable and confident by letting them do it in front of peers, but these peers become peer critics and give feedback to them, because now they know what to look for in an engaging talk. So engage the audience, learn how to be more comfortable and confident by practice, and learn how to read nonverbal cues from the audience. Those would be my three.
Okay, thank you. We are getting some questions in from the audience, but I'm going to go through 2 more rounds of questions, and then we'll take additional questions from the attendees. So, Ravit, what are some like practical strategies, approaches, you know, actual activities, as it were, that you can use for your goals, to attain your goals?
Right. So we have, I mean, we've developed curriculum materials for middle and high school students that get at some of those goals that I mentioned earlier. And there are also others in the field that have developed various strategies and activities. So, and again, and just to emphasize, much of what I'm talking about is critical consumption of scientific communication, not so much generation. If people haven't figured it out, I just wanted to point that out explicitly now. So in terms of media literacy, one of the things that we know works is, rather than focusing kids on looking at a website and trying to decide if it's reliable or not reliable by looking at the URL and the font and does it look nice, all things that nowadays could be easily faked up. What actual experts do, experts fact checkers do, and this is work by Sarah McCrew and Sam Weinberg, they've shown that expert fact checkers actually bounce out of the site and try and get information about whether the site itself is credible. Rather than trying to figure that from the site, they go to other sources. That's a strategy that we can use in classrooms and teach kids how to do, rather than focusing on using, you know, is the URL and with .org, .com, or .gov. In terms of understanding the nature of science, helping them, again, see the idea that science as social and working in the classroom as a knowledge building community, where they critique, construct claims, explanations, models, and critique them and scaffold that process. And what they should be critiquing, or the guidelines for critique, should also be shared. So what we do with kids, for example, is we have them develop lists of shared criteria. We call these, for example, criteria for good models, or criteria for good arguments, or criteria for good evidence. And they develop these criteria jointly. They revise them over time. So a criteria for good models, that list might include that the model, you know, fits all the available evidence. There's no evidence that contradicts it. They might say that, you know, it has to show all the steps in the process. It has to be clear and understandable. A lot of them like pictures, so they'll also say, you know, model needs to have pictures and need to be labeled. So that list is something that's public in the classroom, and every time they develop a model, every time they critique others, they use these kinds of criteria lists. Much of what we do with kids in classrooms is that we will have them develop explanations or models for phenomena. So we'll describe a phenomenon for them and give them a set of evidence, and they have to develop models. And if you work in a classroom, there'll be multiple models, right? Because they have multiple ideas about how might this happen. So understanding that in science, there are often multiple live alternative explanations that you have to decide which one is better. And how do scientists figure that out? They use their epistemic norms. They look at which explanation fits better with the evidence. And another important point is that we give them evidence that varies in quality and strength. So it's not vanilla, clean, what we call hygienic evidence. Rather, we mess it up a little. We engineer into the evidence the kinds of problems that you might see. Lack of control, sample size is inappropriate, the person who did the study does not have relevant expertise, and so on and so forth. So the evidence is what we call epistemically messy. We make it more difficult rather than easier, because that's what real evidence looks like. And so they have opportunities to work with this kind of messy evidence with alternative explanations that they have to decide which one is better. in a community, classroom community with shared norms. So those are some of the key features.
Excellent. Thank you so much. Mary, how do you implement your learning objectives in terms of strategies and approaches?
So I teach such a range of classes that I'm going to do very kind of broad brush response to this. So classes range from an introduction to science communication, which is just really introducing students to what they don't know what science communication is. And that term itself, as Nick and Bill and I use for the initiative, hides a lot of what it is. So for example, Bill Hallman, who's on the call here, he is a risk scholar, and so risk communication is his area. Nick works with has worked in immunology, and he works with graduate students. I'm a biologist. Ravit works with young children science communication. So science communication is just such a broad topic that it's so many things in there. So when I think about the classes, again, first, everything is based in active learning in the sense that it's not about necessarily sitting in the seat and having a lecture, but it's about the actual doing of something. And I always tell the students, you're going to remember me because I bring crayons into the undergraduate classroom, because the one thing that we need to recognize that I see a lot of students who are terrified of science. They've been told they can't do science. It's too scary. They didn't have a good experience in the science classroom. Last week, students were talking about the fact that in their undergraduate, the teachers only cared about getting the correct answer versus actually doing science, which is messy and uncomfortable, and it's not always clean, but it's always engaging if you just let go and just engage with doing real work. So we do try to do real work, but I also often try at the beginning, I'll try to couch it in activities that seem less threatening. So if we are using crayons in the classroom to draw a picture of a scientist, and then we can discuss why do you have that particular perspective of a scientist, then they can start to unpack why they think a scientist looks like Einstein versus looks like Mae Jemison. Why are we assigning those kind of filters to it? So then we start to engage with real science. They meet scientists, they interview scientists, they write the comics about the scientists once they've interviewed. They read real science papers, but they also read science written for the lay public, which is the non-academic public. They look at science in a variety of formats. They read science in a variety of formats. We look at movies, we break down movies and try to understand how the science has been presented. We talk about different methods for collecting information for the public about their perceptions, and then they actually practice those methods. So they're actually doing surveys, or they're doing face-to-face interviews, or they're in some way engaging with the public so that they can see how people communicate and feel about science. And then we do, discussion is really key for my classes, because if from the comfort of a classroom space, you can engage other people and recognize that you can challenge someone else's belief in science. You can kind of do that anywhere else. So I think those are my primary strategies, with the idea that we go from developing the comfort to having some level of expertise in terms of actually communicating science.
Thank you. All of these classes sound very fun and engaging. And Nick, will you want to share how our courses run? And also, while you're at it, Bill has a question about the Improv to Improve workshop in terms of details about costs and time, et cetera. But please first talk about your communicating science class itself.
Sure. So in addition to the typical lecture format where we give them the principles, it's a lot of learning activities where they work with each other, they work in small groups, and they work alone, giving these 3-minute speeches. But this one small group activity that we do is, I've really mentioned knowing your audience. We give them different audiences. How do you talk to PTA meeting? If you were going to go tell a PTA meeting what you do, how would you do that? or you know, a group of MDs, if you're going to tell them about a new drug that you're working on. And you know, it forces them to think, well, you know, what do these people really care about? What are their values? What do they know about what I'm going to tell them that I can use to help them understand by various ways of example and analogy and metaphor. And so that's one. We also ask them to give their 3-minute speech to each other to practice. But now we ask them to turn that into an elevator pitch. Tell them in 30 seconds, the time it would take to go from the first floor to the 8th floor. If you're with the CEO of a company, how would you introduce what you're doing in a way that is so compelling that he invites you to come to his office or her office to tell me more about what it is you do? It sounds fascinating. So those are some of the things. And the class itself is so diverse that it's a learning experience there. We have plant biologists to civil and chemical engineers.
Aeronautic engineers.
So it's very, very diverse. And the whole idea is they have to explain to people outside their field what it is they do. And the control in the room, our control is Dave. He's not a scientist. And if he doesn't understand a word, he'll call a timeout. What is that? I don't understand what oligonucleotides are. How can you explain that to me? And it forces them to think, well, if he doesn't understand it, how am I going to explain it? So those kind of activities help them engage.
Thank you. Do you
Thank
want
you for the aeronautic engineer.
Sure, it's a mouthful. Do you want to just quickly, since you have the mic, talk about the Improv to Improve workshop, and if somebody were interested in that, what are the details in terms of?
Sure, happy to. We have a problem in that everybody is interested in, oh yeah, come and give a workshop. Well, it's not a one-off. You don't teach how to do this in one session. We'll come and give you a teaser workshop where we go through some of the content and some of the activities that we do in the course, but it's a commitment. If you're really, really interested, then it's once a week for 3 weeks at 3 hours at a clip. And the in-between time, you get homework. You have to come prepared to the next week's session to do it. We don't have a pricing scale. We kind of work with people to see if we can get out there, but it's a few $1,000s for the full workshop series.
Thank you.
Call Mary, she can tell you more.
I'm going to continue to ask some of the great questions that are coming through. Maybe Mary, you could take this. What are the particular communicating habits or behaviors of experts that distance them from the layperson and muddles their messages?
Well, and I think I probably am saying what Nick would say to some of this, is that scientists aren't trained to communicate except within a very bounded set of practices and formats. And what I do find is that Rutgers students in particular, at their senior year, scientists, biological students in this case, very focused, is that they communicate incredibly effectively within the discipline. They have been working with a format, it's very structured, it's very organized. And so they're good communicators within, but when they leave the discipline and attempt to talk to somebody, they forget that the person they're speaking with doesn't necessarily understand the words, that is the jargon they're using, doesn't understand science, doesn't like science, and they don't understand why it's important. So I think for scientists, it's not necessarily that they are bad communicators to start with, but they're trained in a very specific way. And that way doesn't translate to people who don't, as Ravit referenced earlier, understand the scientific process. So that's one. there's not a lot of practice at all, even in terms of speaking science, which Nick talked about, because for undergraduates and graduate students, it's not until really you're a graduate student then you're actually speaking to people in a public forum, but that's a public forum of people like you. So the things that make, or the factors that make a scientist not communicate well, we've kind of really referenced it already in this flow from K to postgrad. And the reason they don't speak well, or they don't communicate well to a non-science audience, is they have never been even alerted to what you need to do. They think everybody will listen to me. And that goes back to, I had to learn that as a scientist when I worked in at a museum, and just didn't get why everyone wouldn't want to read a science textbook, because I love them. No one ever told me. So, it's not part of my vocabulary as a communicator. So I think that's primarily it for me, Janet.
Thank you. Ravit, can you tell us a little bit about how we should incorporate climate change education into the K through 12 classroom, as New Jersey is now the first state to mandate this?
Yeah, so I mean, the climate change has been incorporated into the NGSS standards. It was there before, it has been amplified. I think that there's some basic content understanding around earth science that students need to have. That's not my area of expertise specifically. I'm a life science person, but and that's embedded in the standards. I think one important thing to understand about the standards is that we are no longer just teaching content. Those days are done. We are teaching scientific practices, and the kids are learning the content by engaging in scientific practices, as do scientists. So we want the science classroom to reflect more of the scientific process that Mary was talking about, to reflect a better understanding and engagement with, so working knowledge of scientific practices. What do I mean by scientific practices? So scientists generate explanations. Most of these are in the form of models. If you open a science journal, you will see those models in there. So we engage kids in developing models. They work with evidence, they argue, they communicate. Those are, there are a set of 8 scientific practices: asking questions and developing explanations and arguing and modeling and that data analysis and designing investigations. All of that is part of it. And so the learning of the content does not happen through lecture. The learning of the content happens just the way scientists develop knowledge, through engagement in these practices. So whatever you're doing with climate change has to be in that flavor. I think another important point about climate change that goes back to my point about understanding the social nature of science is understanding consensus. So one of the things you see is a scientist or two who are arguing against climate change, and people are picking that message up and running with it. And a key part of what's missing here is not understanding that when the scientific community reaches a consensus on something, that is a hard achievement to come by. There are not a lot of things that there is such strong consensus around in the scientific community. So it is not the case that just because one scientist or two scientists or a small group of scientists arguing against something that means that it's a contentious issue and we don't know where things are. So helping students understand that, and this goes back to the trusting the experts, I think is a very important part. And for climate change, it is particularly pertinent. I think another thing that people can do in classrooms is work in the local context. What are some things in the kids' communities that have been affected by climate change, that affect climate change? Ground the science learning in phenomena and problems that matter to the children. And one way to do that is by working within the local context that they're in, right? Their own communities.
That's another version of knowing your audience, in the sense that what's important to them, what's important to the listener, the receiver of the information, and how can you make it relatable. So Nick, there's a question about writing. When we say communication and differentiating between writing and communication, when we have a lot of support for education in terms of writing, particularly at the graduate school level, but not much in the way of training in communication. So when you use the word communication, what specifically are you referring to? Just oral or written as well?
Well, I think, as you said, there are plenty of opportunities to get help. How to write a grant, how to write a paper, writing workshops. They crop up every couple of weeks. There are those kind of opportunities. Plus, whatever you're getting in your graduate program, they have to write a manuscript or a grant application as part of their candidacy examinations. So we do some writing in the communicating science course, but we prefer by design to focus more on the oral communication, where there isn't as much opportunity for that. You know, everybody, all the students get up and give a talk, and they give a talk primarily to their lab groups on a regular basis. These are people in their own discipline. They can get away with using jargon because everybody understands the jargon that they use in that particular small circle. But they don't have practice with diverse audiences. And I think that's the key to learning how to communicate. You're out of your comfort zone. And that's where the improvisation comes in. I don't know if everyone has tried improvisation. It will take you out of your comfort zone. But once you realize the value of learning how to appreciate, in this case, talking to an audience that is outside of your discipline, I think you understand how improvisation can help. So I don't know if that answers the question sufficiently, or.
I think that's excellent. Thank you.
Okay.
So Maria, hi Maria, asks, and this can be for any of you that has a response. Are there any structure/processes that you find effective for teaching scientific communication, similar to the 5 whys and 1 how, or the and, but, therefore narrative?
Yeah, I'll take that. The and, but, therefore is great, because most talks are and. I did this, then I did that, and then I did this. But the and, but, therefore, we did this, but something went wrong. I mean, it's not a crime to get a bad result. It wasn't what you expected, but you should go with that. Go, why? Why did you get the bad result? Why didn't it turn out the way you expected? Therefore, we changed the design of the experiment. And that's acceptable in a talk. I mean, that led you to a new direction and maybe a new discovery. So, and, but, therefore, that's the equivalent of in the actor's playbook. Yes. The actors never say no. They always say yes. Yes, and they go on to something else. But the and, but, therefore is valuable in terms of getting your points across.
Thank you. Anyone have anything else to add? Or?
I want to second something really important that was said here, and that when scientists are communicating with lay audience, especially if scientists are going into K-12 classrooms, I think that telling the whole story and the human perspective the creativity is absolutely critical. I think that making science look like this very hygienic, clean, objective process is both disingenuous. That's simply not how science works. But it also, it's something that I think can make certain groups of people feel that they do not have a place in science. Students that value creativity see science as, well, it's not creative, and that's just not the case. So I think telling the whole story, what worked, what didn't, showing the thinking process, that you got feedback from someone and decided to change, or presented it somewhere and people had this critique and then you decided you had to do this and that. I think telling that whole story in a more nuanced picture of what science is like really is absolutely important.
Thank you. So there's another question related to the learning objectives that you each articulated, and the kinds of reliable and validated survey tools or instruments that may be available to assess those learning objectives. For example, assessing the quality and strength of evidence, assessing someone's level of critical thinking, or assessing the ability to vet media reporting about science, or even determining who is a lay scientist versus a professional. So what are the kind of tools and instruments that might be available to people to assess those questions?
I'm not going to answer it completely, but there are tools that exist, and I think it's called PairWeb, where you can find a lot of different survey instruments, validated instruments that can be used to assess a particular aspect of what some of the things we talked about here in science communication. So you can talk about identity and interest, which are really key factors in someone engaging with science, whether it is as a vocation or an avocation. So I don't necessarily use a lot of these evaluative tools in the classroom setting. I use them in my research when we're looking at how people understand science, whether it's students or K to 12, or whether it's adults. So I'll use them there, Jenna, but not so much in the classroom setting. In terms of it being evaluated, how the students did, for example, on the media reporting, that becomes something where students work together with each other a lot. There's a lot of peer work with that is not going to answer the question quite as Lynn asked it, but
yeah, I guess maybe one of the questions is another way to phrase this would be like, how do you teach somebody when something has been peer reviewed, or how do you teach somebody how to determine the level of audience that they're speaking to or engaging with? Maybe that's a better way to think about it. So.
Well, I mean, I can talk a little bit about the audience. Some of that is just getting people to think about the fact that the audience is not me, and to go beyond what they believe is the way to do something versus to actually spend some time with who is your audience, what are they like, do some research. There's a lot of different surveys out there that talk about particular demographies and what they believe and what they know. So some of this is really more getting people to think about these issues and these factors rather than necessarily having them, a tool that can measure their success. Because if you never think about who you're talking to, you're just going to say it the way you feel comfortable. And I think you and Nick and I talk about this in the graduate classes. How do you take a scientist and get them to understand that you can reframe or restructure your message to audiences based on what they know, what they're like, and you will still get the same message across, even though you're not using the same words.
Right. I mean, I think that I do not know of specific instruments that do this, partly because some of these ideas are relatively new ideas in terms of K-12 education, thinking about evidence quality, evidence strength. It's not something we've been doing. So there are, and assessments usually follow much later in terms of the research agenda in education. A second second issue is that none of this is easy to assess. I mean, the idea of critical thinking has been around for a very long time, and yet we don't have good instruments for evaluating critical thinking, especially not a survey kind of instrument. It's just not conducive to evaluating something as complex and somewhat ill-defined as critical thinking. Something like evidence strength, well, that really depends on the discipline, and in many cases, the subfield. What one scientist would consider criteria for strong evidence may vary from one field to another field, and it's entangled with disciplinary knowledge. So it's unclear to me that you can really have domain general, sort of science general instruments that get at some of the ideas around evidence, quality of evidence, strength. I think those are very much disciplinary specific, and we have yet to do, we're starting to do that work, but we've yet to do enough of that work to have some solid and reliable instruments for it.
I mean, I think something maybe even as simple as teaching students how to do a search using trustworthy search engines and PubMed, and, you know, finding the original sources, maybe something along the lines of what we're trying to get at here. Bill has a question. How do you think about the importance of understanding uncertainty as an essential component of the scientific process and science communication more generally? For example, communicating what is not and what cannot be known. So how do you deal with uncertainty?
I will start, and then I'm sure
Yeah, go ahead.
everyone else will have something to say. And I think this goes back, way back to the beginning, and Ravit's comment again about nature of science is, what is science, what can it do, and what can it not do? And that's one of the baseline fundamentals that we often talk about in the classes, because, and I often ask, what's the oldest science communication column in the mass media, and they'll come up with different things. But if you think about it, the astrology column is considered by many to be the oldest scientific column that we see in newspapers, and yet it's not science. But you know, this idea of getting people to understand that science is a way of thinking about the world, that there are other ways of thinking about the world, but it has limits to what it can and cannot do. In terms of uncertainty, that's absolutely critical for people to understand in science, because I mean, we can just look at the last 8 months, uncertainty from the beginning, you know, where scientists have been trying to develop the knowledge about COVID, and it's been a moving target. And I'm sure everybody here is nodding their head saying, yeah, I know today it's this, tomorrow it's that, and then it's another thing, and then it's something else completely different, and I don't know what to believe anymore. And if you don't recognize that uncertainty is part of the scientific process, you're never going to be able to really accept someone communicating to you. You know, it was easier when it was that eggs were good, eggs were bad, eggs were good, eggs were bad. COVID is a lot more frightening than the media's coverage of what was good and bad to eat. So that's absolutely a critical thing to make sure you train people.
Anyone else have anything to add?
I can add a little bit to that. I think that's very important. And I think this is something that relates to responsibility, and whose responsibility is it when we think about communicating. I think it is absolutely imperative that scientists are careful in how they communicate information. I think that getting the message across is very important, but that cannot come at the expense of having that message be oversimplified or communicate with a degree of certainty that just isn't there. And that happens sometimes when information morphs from the lab to the media and social media, where some of those qualifiers that we use as scientists when we write sort of get thrown out of the sentences, and the sentences become much, much stronger than what the research actually showed. And a lot of the contextualization disappears as well, and that's a problem. In terms of consumers, we have to help students understand what uncertainty means, that these hedging and qualifications are not an indication of I don't know. right? They just help you bound what we do and what we don't know. There's been research that's shown that when people read information that is hedged, they tend to assume that scientists just don't know, right? But but you can counter that, right? You can fix that essentially by helping them understand the nature of science. And then they develop a different perspective, a different stance towards uncertainty, and no longer view it as scientists don't know what they're talking about, especially what Mary said with the information around COVID. It's not the case that scientists don't know what they're doing. It is the case that the situation is evolving, our knowledge is growing, our understandings are changing, and that's a good thing. And that's something I think we have to teach. We have to.
Right. And when things are later proven different, it's not that we were wrong at the time, it's just that we didn't have all of the information that we then later had in order to interpret the data, reinterpret the data. So another question I have is, what do teachers need to know about science in order to help their students make sense of science? So we want to encourage, people who are not necessarily scientists themselves to then teach kindergarten through 12th grade, for example. What should you emphasize as a scientist talking to kids, and how should we help? There's two parts. As us as scientists, when we talk to kids, what should we emphasize? And how can we help teachers who are not scientists themselves feel comfortable teaching? I guess that's for Ravit.
Yes, I can take that. So I think it starts, it's a road, right? So first of all, we need to help teachers develop an understanding of nature of science. So, right, kids get from teachers what teachers know. If teachers have a view of science as this linear process that's unproblematic, where if you get something wrong, it's because you made a mistake, right? There's some error that you did, and that's why the answer is different. That's not the case. So if we can help teachers understand nature of science, and that in my mind falls both on them when they're students in K-12, but most importantly, when they're students in college. So when we have college labs in which you follow a recipe and get a particular result, and you know darn well that if you didn't get the result you're supposed to get, it's because you made an error. That's problematic. So we have to have the messaging, the epistemic messaging in our undergraduate courses has to reflect the way scientific knowledge is developed. Points like uncertainty, for example, that has to be part of the game and what they do and what they learn about in college. So that when they get to me, because in New Jersey, teachers are required to have a bachelor's before they get into learning how to teach. When they get to me, I can amplify that messaging. And then what I do in my role is I help them understand how to help kids understand that. But if I have to do the double work of also helping teachers understand it themselves, which I currently do, that there's only so many things you can fit into a teacher preparation program. So it'd be tremendously helpful if some of that work could be done, K-16. I think that's something, media literacy is something that teachers don't necessarily get. I think another very important element in understanding this is also understanding the role that science has around social justice issues. So one of the things that I do with my students, for example, is we look at how the way we teach genetics essentially amplifies kids' existing deterministic and essentialist views. So these are views that see genes as directly related to traits, meaning you have the gene, you have the trait. And therefore you cannot change anything. If I have a gene for a particular something, that's who I am, that's what's gonna happen. And essentialist views are ideas that particular groups that have particular genes are gonna have particular traits. So different races, for example, and this is not true, right? Just to be clear, this is not true. This is what people think that's wrong. The particular races have particular genes that result in particular behaviors, both physical and other kinds of behaviors, complex traits like educational attainment. And the way we teach genetics pushes towards those kinds of essentialist and deterministic views, okay? And so that's something that we can combat at K-12 and K-16. Another important point is understanding how science has contributed to those kinds of views. And this relates to science communications. When scientists say there is a gene for X, a naive listener hears it exactly like you said it. There's a gene for X, meaning if I have the gene, I have the X, and there's nothing in between that mediates it. So I think that the teachers need to understand the role science plays in culture and society, and the way culture and society play into science. So the kind of science that kids are getting in school are colonial Western science. We never actually call it that, but it is what it is. So we need to be thinking about those issues too if we want to promote equity and social justice. And that's something that we've been beginning to grapple with also in teacher education.
Thank you. Zania asks, getting good data costs money. We all know that there, and Nick, I think this might be one for you. We all know that there are gaps in our knowledge. So how do we explain how investment in science helps us to collect data that changes our understanding?
Well, I think it goes back to what I think Ravit said at the beginning, that I think we first have to teach lay audiences how science works, and it's evolving, so that as you get more data from experiments, you modify your conclusions, so that the only way you get more data is to have more investment in the research enterprise with your favorite philanthropic group, disease-oriented, NIH.
Taxes.
I'm sorry?
Or your taxes, right?
Taxes from the government, sure. But until you're never going to get a complete answer, because new evidence will be applied to the conventional conclusions that we deal with at any given moment. So the more money that is invested in research, the more data, and hopefully the answer is more accurate.
Thank you.
There's a couple of questions in the chat box. I don't know if you want to go to them. And I don't want to be, it has to do with how we measure improvement in the communication skills in our course. And I should have mentioned this when can I answer that question?
Sure.
So we have a colleague in the School of Communication and Information who analyzes videos that our students make, one at the beginning of our course, giving this 3-minute speech, and one at the end of the course, giving the same 3-minute speech, hopefully in a better way from all of the activities that has intervened in terms of learning the principles and practicing some of the activities. And everybody starts at a different level. His area is public speaking. So they have a rubric that they use to score speeches. And he applies that rubric to our students who give 3-minute speeches. They get back a score at the beginning of the course and comments, and they focus on some of the ways they could improve. And as they apply those the activities we're teaching them to that 3-minute speech, give it again, although they all start at a different level on a scale of 1 to 100, they all go up, usually by 10 points from the beginning to the end of the course. So that's the metric we use. And I think that's really, other than the consensus of people listening in the class, because we look at the videos before and after, and everybody agrees it's pretty good after than before. So I think we're doing okay.
And how can people continue to improve their science communication skills throughout their career? What are some activities that people can be involved in?
Practice, 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 practice. That's my mantra. I
No,
mean, there's plenty of
on a
opportunities.
daily basis, like practice to whom? Like how can you?
Yeah, I mean, PTAs, they're always looking for speakers, Elks Clubs, BPOE. Elementary schools are a great place. I used to go to my kids' elementary schools all the time, every year. And I got to tell you, years later, one of my son's classmates would come up and tell me, "Wow, I really understood what you were talking about. I brought a human heart into the classroom and explained to them how it worked." I mean, it's just they're like sponges. I mean, elementary kids are great. Unfortunately, they ask the most difficult questions as well.
Let's not forget social media is a great place for scientists to be engaged with the public. We had a speaker a few weeks ago from Rutgers who talked about his social media communications about COVID, and people who attended the Science Cafe wrote, "Thank you so much. It's so great. Now I'm going to follow you because you are explaining this to me and I trust you. You demonstrated your expertise." So social media is really important for scientists to consider communicating outwards.
Thank you so much. And I think our time is up, so I will turn it back to Bill Hallman to give us some final words.
Great. So thank you, Doctors Duncan, Ponzio, Nucci, and to our moderator, Dr. Alder, for a really interesting talk. I want to thank my students who all logged on as me. I do not have 9 different personalities. I managed to forward my login instructions to my students in the risk communication seminar that I teach. So just to explain that I don't have a split personality. Really interesting conversation. Mary, do you want to put up the final slide? I do want to invite you to the 4th seminar, which is coming up on December the 8th, where we will talk about science communication in the wild, engaging diverse audiences with science. I hope you will join us then. Until then, thanks very much. There will be a recording of this and, of course, all of the other sessions that you can access, and you can register for the future seminar at scicom.rutgers.edu. So thanks very much and have a great evening.